So let's look at the example here, okay, where actually you were given a butane at 360 degrees Celsius, okay, this is butane. So let's say this is ST and you have 3 atmosphere, which is, this is your P, absolute flows into a reactor at a rate of 1100 kilogram per hour. You are required to calculate the volumetric flow. So what would be the V dot of the stream using conversion from standard condition? So you just need to use standard condition. So how do we do that? Again, we just need to rewrite back the equation. So the equation is such that PV star equals divided by PS V prime S equals to N T divided by TS. TS, VS and PS is considered as the standard condition. Okay, so if you can remember, this value is actually 0.02214 meter cube. This one is 180 M. This one is at actually 273 Kelvin. Okay, so now you were given the you can determine the value of N actually. How can you do that? So this is supposed to be N dot. N dot is equals to M dot divided by MW. Okay, so M is actually 1100 divided by the butane molecular weight. So it's supposed to be 48, is supposed to be 58. Then you'll be able to get the N dot value. Okay, so this is supposed to be 19.0 kilomole 19.0 kilomole per hour. Okay, and then you know the temperature is actually 360 plus 27360, and then you know the pressure is at 3 atm. So when you substitute all this information, then you'll be able to determine your volume. Okay, you'll be able to determine your volumetric flow rate, which is equivalent to 329 meter cube per hour. Okay, so you can observe at this calculation and then you may try to do it by yourself. So let's look at the next video, and we're going to see some other information that is needed, that we need to know, especially on the ideal gas mixtures. If let's say now you have a mixture of gases, not only one single gas, so how do we solve the problem? My next question to you is, does the gas flow in the chemical plant is of a single gas? What if there are mixture of gases in a pipe? How do you estimate the properties? So this will be our challenge. If let's say, because usually in the single stream, you wouldn't find a single gas inside that. There are actually multiple gas, and then how do we estimate the properties of the gas? How do we estimate the density of the gas, for example? How do we estimate the what do you call that, volume, volumetric flow rate, partial pressure, for example? All those things are important for us to determine. Okay, let's now have a look at ideal gas mixtures. If you have N1 mole of each species, for example, like this is a species of the gas, you can try to calculate the pressure or volume of that species gas alone. Okay, if you have only one. But now, if let's say you have a substance of A, and then you have a substance of B, and you have a substance of C, which are contained in a volume of V and a temperature of T and pressure of P. So how do we estimate the parameters that we needed to know from here? So let's say that number of moles Na is substance A, Nb is a substance of B, and Nc for C, which is contained in one container with a V volume at certain temperature, which is T, and at similar pressure, which is P. So we can say that the partial pressure and pure component volume Va are defined as PA is pressure exerted by number of A moles only at V, T, and P, and VA is the volume occupied only by number of moles of A, okay, Na moles at VTP. What does it mean here is, if let's say you have a component, okay, so there are some gases here, okay, so you have gases which is and then let's say I draw a lot more. and you have A here, another A, and then this is B, this is gas B, this is molecule gas B, and the remaining is C, for example. Okay, so what does it mean by partial pressure of A? Means that it is the pressure that is exerted only by this A component, by this mole of A. And what does it mean by volume of VA? Okay, the pure component volume, it means that the volume which is only occupied by this species gas of A. So similar to B, similar to C, it means that if let's say you are mentioned, okay, what is the partial pressure of C? So basically we just calculate the pressure exerted by these molecules of C, okay, at the container wall of the gas. So that is what actually we calculate as partial pressure for a certain component. So for ideal gas mixtures, if let's say we have a partial pressure PA, which is refers to the pressure that will be exerted by the species, okay, this is what has been defined earlier. It refers to the pressure that will be exerted by a species. For example, if let's say PA means that a species of A, if there were no other species present. Okay, and the pure component volume VA, it refers to the volume that will be occupied by a species. In this case, we are using A, so it refers to the species A if there were no other species present. Okay, so imagine macam ni lah. So if let's say you have three type of molecules, okay, this is, let's say this is C, and then this is B, and then this is A. Okay, so when we mention about the partial pressure of A, it means that whatever that species, this species of A exerted the force, okay, and when we mention about pure component volume of A is something that we only measure this way. But in reality, okay, which is in reality, your A can be actually here, it can be actually here, it can be actually here, it can be actually here. It can just be, simply, it is because the gas just move very fast and they just move around very fast. It doesn't stick at one place. Okay, so you want to mention but then this is a pure definition to you so that you know what does it mean by partial pressure as well as pure component volume when you're being asked later. If the individual mixture components and the mixture as a whole behave in an ideal manner, okay, this is what we call as ideal gas mixture. Okay, as long as it is behaving well. But if there are a number of more of all species in the V, T, and P, then PV equals to nRT. Okay, but if let's say you just want to calculate the volume or the number of mole of A only, you can just use the partial pressure of A instead of using the total partial pressure. So you can use this component, substitute the number of mole of A, then you'll be able to determine the partial pressure of A and the other way around. So when you divide these two equations together, okay, PV nRT as well as PAV equals to NART, then you'll be able to simplify everything. V is cancelled out, temperature is cancelled out because it is within the same volume of container, it is within at the same temperature, so you can cancel it out. But now you can just have a partial pressure of A divided by P equals to number of A divided by the total number of moles equals to YA. So YA is actually the mole fraction of A. So this is how you get the term of YA. Okay, we call it as the mole fraction of the gas component. Okay, and usually we use X for liquid phase, and usually we use Y for the gas phase. So in this way, the sum of the component pressures, partial pressures or volume should sum to the total pressure or volume. So if let's say you have a partial pressure of A and then you also determine partial pressure of B and C and so on, if you add all together, you will just get the total pressure. Similarly, with the pure component volume, if let's say you have VA, you have VB, you have VC, etc., then you'll be able to get V. V is actually the volume of the container itself because, yeah, when you add up all the gases together, of course, it fits into the container itself, so it gives you the volume of the container. So if you divide either the partial pressure equation or the pure component volume for the total mixture, so if let's say you have PAV divided by PV equals to NART divided by NRT. Okay, and you have PVA divided by PV equals to NART over NRT. So you just see that it's just similar expression, except that now this term is actually represented by pressure. This one is represented by the component volume. And you can see that in terms of the relationship, is this just the same. The relationship of this is just the same. Okay, this is the same. Okay, so you can see that this is directly proportional, or that it is directly related to each other. Okay, so we note that the term RT cancels in both equation, and that V cancels in the first and P cancels in the second. Also that NA divided by N equals to YA. Okay, so if you look at the previous equation, okay, here we can cancel just the RT here. Okay, so this cancel, this is cancel. Okay, and then in the first term, this is cancelled to each other. So you have PA over P equals to NA over N. And here you are cancelling P, and then you're also cancelling RT and RT. You also get VA over V equals to NA over N. Okay, so when you, and then you know that, okay, YA is actually NA over N, which actually we have defined earlier in this phase. NA over N, okay, is equals to YA. So when we know that YA equals to NA over N, then we simply can substitute in this particular equation. This NA over N is actually YA. So we know that YA is equals to PA divided by P. So if let's say we want to determine the PA, the partial pressure of A, is just simply PA equals to YAP. Okay, does it make sense? You know, because PA over P is equals to NA over N, right? And then you know that NA over N is equals to YA. So PA is equals to YAP. It's very simple. So similarly for volume, you can also do that way. In order for you to determine the pure component volume of species A, you just need to include YA, the mole fraction of A, okay, multiply with the total volume. So you'll be able to get that VA value. So the volume fraction as well. So as I mentioned earlier, the volume fraction VA over V, or pressure fraction PA over V, is equals to the mole fraction. So VA over V equals to NA over N equals to YA. Similarly, PA over P is equals to NA over N is equals to YA. So that is the relationship between the component, the component of specific component. When you want to determine the number of moles, or determine the partial pressure, you want to determine the volumetric flow rate, volume component, pure component volume for the gas. So you can use this kind of expression as long as it is an ideal gas. Okay, so that is very important for us to really know. This is the parameters that we can use in order for us to estimate what will be the, if let's say we have a mixtures and it is an ideal gas mixtures, how do we estimate the properties inside that particular mixture? Okay, so this is some of the equations that you can use. So kalau you ada B, if let's say you have a B, component B, it's the same thing. So PB is equals to YBP, right? And VB is equals to YBV, sorry. Okay. So we come to the conclusions. So here you have learned a little bit on the mixtures of ideal gas and estimating some kind of properties, parameters. For example, for densities of liquid and solid, it's fairly easy because it is independent of temperature. Then you can just use several methods in order for you to solve that. And other things, you also look into gases, because gases, it's actually whatever the volume is, actually it fill up the container volumes. And when you have a mixture of gases, there are ways for you to really estimate the properties. So that's all for this time. Thank you very much for watching. Assalamualaikum warahmatullahi wabarakatuh.